All right, we're going to talk about oil analysis, and we'll keep right on moving here. Oil is the lifeblood of many systems. Oil analysis is like a blood test. A sample's taken, samples documented, samples delivered to the lab, tests are performed, results are interpreted, and diagnostic report is issued. I'm 65 years old. When I turned 50, I decided I needed to get a full-blown physical. Our family has a history of heart disease. And so I went in, and what did the doctor do? Dr. Jennifer said, Henry, we're going to take a blood sample. So they took the blood sample. 2 weeks later, I go back, and she says, hey, here's what's going on. Your cholesterol, your good and bad's out of whack. Your triglycerides are out of whack. You're overweight. Just all these things that she saw, based on my blood work. And she said, I'm going to have to make some changes for you. Okay, so I knew about the cardiac stuff. I knew all that stuff. Our family had a history of that. But then she got my attention. She said, your A1C is high. How many people know what an A1C is? Okay, it's for diabetes. Okay, and that's the first I'd heard of it. So she said, your sugar level's high, your A1C's high. She said, I can give you stuff for the cardiac stuff. I can give you something for your high blood pressure. I can give you something for your cholesterol, something for your triglycerides. You're too young to start on diabetes medicine, so we're going to change that with lifestyle habits. You're going to get into diet soda instead of regular soda. Don't drink sweet tea. Get off the chocolate, all these kind of things. And so much, exactly what happens when we send in, or you send in an oil analysis, okay? We give you recommendations back. This is what you need to change to bring your system back to normal. So I did this for 5 years. Every 6 months I'd give her blood work, and every 6 months my A1C was hanging right where it should. We were doing great, doing great. Well, like I said, it had been 5 years, so I decided, you know what? I've been a good boy, and I was in the store, and I saw this box of Krispy Kreme donuts. Everybody ever had Krispy Kreme donuts? So I love them. I thought, you know what? I've been a good boy. I've watched my numbers. I've done what Jennifer told me to do. And so I got a box of Krispy Kreme donuts, and I tell people I went home, and I said I ate 11 of them. I said the last one I just took and just rubbed all over my body. And I really enjoyed my donuts. Well, the bad news was I had to see Jennifer in 2 weeks for another 6-month blood checkup. So I get that, and I go back 2 weeks later to get the results. Jennifer flips up the laptop. She's looking at it, says, oh, your cholesterol looks great. And she's telling me all these good things. And before I got there, I told my wife, I said, wouldn't it be funny if when I sit down with Jennifer, she can tell that I had donuts? And my wife said, she can. I said, no, she can't. She said, yeah. She said, that A1C, and I see you nodding your head, that A1C we'll see back 100 days. I said, yeah, but she's not going to be able to see that. She said, I'm telling you. So Jennifer's looking, and she says, Henry, she says, everything looks great. Your cardiac stuff looks great. But your A1C, there's a spike. And it's usually when I see a spike of this intensity, there's been a high sugar intake. And most oftentimes in the last, if it's within 2 weeks, it's somebody's had donuts. Have you had any donuts in the last 2 weeks? I said, yes, I have, but there's no way you can tell that. And she said, well, it's right here. I'm looking at it. And I looked at her, and finally she started smiling. I said, what's going on? Well, you know what happened. My wife had called her before I got there and said, Henry's coming in. He's had donuts 2 weeks ago. So they had me going. So I tell that story to say, okay, here's the power of oil analysis, what we're going to talk about now. Could Jennifer tell there was a spike in my sugar based on blood analysis? Absolutely. Could she tell it was caused by donuts? Absolutely not. If you give me a heavy-duty diesel engine that holds anywhere from 11 to 14 gallons in the reservoir, and let's say a thimble full of coolant has leaked into that reservoir, into that engine, we're going to see it. Even that small amount, we're going to see it. And it's going to show up as what? Sodium and potassium. And it's going to show up as a spike. And when we see that spike and we see that it's sodium and potassium, we know that the donut is what? The donut is coolant. Okay? So there's power in the oil analysis. Now what I'm going to do is I'm going to walk you through some of the different tests. And it's not important how we run the test. I mean, it is important. We want to be accurate, we want to be reliable, we want to be timely. I say there's an art to analysis. Accurate, reliable, and timely. But what's important is we want to make sure that we're being proactive with it, okay? And so I'm going to talk about the test, but what's more important is I'm going to tell you how you use that test when you're looking at data. You know, what's a good number? What's a bad number? Okay, what's a severity 1? What's a severity 4? And we're going to give you some of those guidelines, and then by the end of the day, we're actually going to do some data interpretation where we're going to look at it and we're going to say, okay, this is alumina silica going up, that's dirt. Okay, this is sodium and potassium coming in, that's coolant. We've got oxidation nitration increasing over here. Okay, we've overheated that component. So there's things that we're going to look at. So when we do oil analysis, we're monitoring the condition. It's condition monitoring. What's the condition of the oil? What's the condition of the lubricant? So when we look up here, we're looking for wear. When you look at a report, you see 24 elemental metals on that report, in the middle of that report. Most labs run anywhere from 20 to 22. We run 24. One of those that we put in there, trying to think what it is, manganese. We see manganese in gears. So anytime we're looking at something that has gears to it, we want to see manganese. That's an indication that we've got some gear wear. So we're looking at the wear in the sample. Then we're looking at the lubricant properties. Okay? Is it maintaining the viscosity? Does it still have a substantial additive level in it? Is it still good for continued service? And then we look at the contamination. What contaminants are in that oil? Is there dirt in there? Is there coolant? What about fuel? What happens if we get fuel into an engine oil? What's that going to do to the viscosity? Going to increase it or decrease it? It's going to decrease it. It's going to thin it out. Okay? What happens if we get soot loading? We get unburnt fuel that gets back in there with your EGRs. You see this quite often. What happens with that soot loading? When that soot comes back in there, what happens to the viscosity oftentimes? It thickens the oil. They talk about soot loading, soot thickening. Okay? Then we're going to look for water. We're going to look for oxidation nitration. Oxidation nitration are going to create some acidic byproducts during the combustion process. And those acidic byproducts are going to attack not only the engine components, but the lubricant itself. So we're looking at wear, lubricant properties, and contamination. All right. What does oil analysis tell us? It tells us the condition of the oil. Is it still suitable for service? Okay? Let's not throw away good oil. Let's monitor the condition of it and continue to use it if we can. We have a program, and it amazes me that most of our customers, a lot of our customers are not aware of it. It's called an extended drain recommendation program. You can get extended drain comments from our data analysis team. We've got 10 people that sit in Indianapolis on our data analysis team. If you contact data analysis and say, hey, look, I want to try to extend the drain intervals on my CAT 3516, whatever it is. I want to try to extend my drains, okay? If I'm going to do that, I need you to tell me it's okay. And so we will actually, if you contact data analysis and say, I want to turn on extended drain comments, they will turn them on. And so you will get a comment that says, this oil is good for another 250 hours. This oil is good for another 500 hours. This oil is good for another 3,000 miles. And so by using those extended drain comments, you can find out what your sweet spot is. You know, if you want to extend drains, how far can I go and still have a good lubricant and not compromise that equipment? So think about that. It's a free service. All you have to do is contact Polaris, the data analysis team, and say, hey, we want to turn on extended drain comments, and they'll flip the switch. Determine the condition of the unit. We talked about that, some of the wear particles. And then we want to determine the effectiveness of our maintenance strategy. I taught a class one time in Atlanta, and I said, here's the 3 different maintenance strategies: run to failure, preventive, and predictive. I said, nobody in their right mind runs to failure. I had a guy in there from a third world country. That was their maintenance practice, run to failure. I felt so bad that I said that. But there are times when you run to failure, okay? The component's not that expensive. It's not going to cause you downtime. Boom, boom, boom. You run it to failure, you replace it. Now, what's the difference between preventive and predictive maintenance? Somebody tell me the difference between those two.
Preventive, it's going to be like a strict schedule, like every 6 months you're just going to drain it and then replace it. Or on predictive, you would use the data, determine that's the means between failures, and then go with that.
You teach the class. That was awesome. That's the best answer I've ever heard to that question. It's exactly what it is. It's calendar-based versus the condition of the equipment. I went underground to a coal mine. They said, come down and observe how we take our samples. Tell us everything about what we're doing. So I went down underground. He takes that sample. very tough environment. He did a great job, had a continuous miner, dirty, dusty. Got all the samples taken. There were several samples to be taken on that unit. I said, okay, what do you do now? He said, well, now I go back to the surface. I fill out the paperwork. This is before we had sample submission online. I fill out the paperwork. I send the samples in. I said, okay, then what's the next step? He said, I go back down underground and I change everything out. That's preventive. He said, we do this every so many days, whether it needs it or not. I said, you should wait until you get the results back from your analysis, and that'll tell you when you need to change it out. And I said, why should that be important to you? You invited me down here to tell you that what you should be doing. You've got a competitor down the road at another mine who's also a customer of ours. They're doing predictive. They're going 6 months between oil changes on those units. You're going every month, even if it doesn't need it, okay? So that's the difference between preventive and predictive. Predictive is what we're trying to work with. We're trying to get people to do with the oil analysis. You can go to the table of gifts if you'd like. All right, here's the different types of condition monitoring. When I started with Polaris, I was hired as a field services manager, and they said, Henry, if you want to consider doing vibration analysis, thermography, ultrasound, all these other condition monitoring technologies, if you think that's something that would be beneficial to Polaris to bring in, we're all for it. Well, as I would teach these classes, I would get people in that had expertise in vibration or thermography. And I would ask them, I'd say, help me out here. I'm trying to decide if I should do this in-house or take it out-house. And they all came back and said, you know what? We do oil analysis too. And oil analysis will catch it before any of the other ones will. And I've heard that in the 12 years that I've been in the industry. Oil analysis will catch it first. A close second to that is vibration analysis. And as a matter of fact, if you look at some of our comments, sometimes we'll have a comment that says, we suggest you do vibration analysis and check for a misaligned bearing. That might be a comment. So we know that vibration analysis is a good root cause tool to use out there, a good condition monitoring tool. But all I want you to take away from this chart is that oil analysis will usually catch a problem before any of the other technologies. Okay? All right. It's a little bit after the top of the hour. Why don't we take a break here? I think I've been running you pretty hard through lunch. You guys just had lunch. Take a break here. Let's come back at about 20 after, and then we'll get into the actual tests that we run. But what's important is the values and what they mean to you. Okay? All right, let's talk about testing of the lubricant properties. And these aren't all the tests that we run on the lubricants, but these are some of the most common. Viscosity is the number one test. We always say that's the most important. If you remember back to the lubrication regimes, you got to keep that full fluid film thickness in there, that hydrodynamic lubrication. And then we'll talk about acid number, base number, and then RPVOT if anybody's using it. Anybody use an acid number on your test? Okay, that would typically show up with hydraulic fluids or circulating fluids. Base number, that's going to show up with your heavy-duty engine oils. And then RPVOT shows up with circulating oils like turbine oils, things like that. So I'm thinking in that group we might be able to skip over this. I don't think anybody out here working with turbines, steam generating turbines, gas turbines? Okay, good. All right, so we'll just do the first three here, looking at the lubricant. All right, so for the lubricant, viscosity. It's a measurement of a fluid's resistance to flow, or like I said, a lot of people refer to it as the thickness of the fluid. You know, that's a thick oil, that's a thin oil, okay? So that's the most important test we run. How do we run it? Well, we run it two different ways. We run it, we put the oil sample, the used sample, in a tube, and that tube sets in a constant bath at a constant temperature. The temperature for industrial products or stationary products is 40 degrees C. When we do it for, and that's roughly 100 degrees F. When we do it for mobile equipment, typically like your heavy-duty engine oils, we're doing it at 210 degrees Fahrenheit or 100 degrees C, okay? So that's a constant bath, and so we drop that oil into this little funnel on this tube. It's a glass tube. The oil travels down in the bath, and when it hits S1, we start the timer. When it hits S2, we stop the timer, and then at that point, the system calculates the viscosity of that oil. And the viscosity is based on the time that it took to travel this distance, plus a calibration factor associated with the tube. Different tubes have different calibration factors. So it comes up with the viscosity for that oil. And like I said, it's at 40 degrees C for stationary industrial equipment, and then it's at 100 degrees C for your mobile equipment. Okay? Now, been having a conversation with these two gentlemen over here. They've got an oil analysis report that's coming back flagged as a severity 4. We got to looking at it. On the stationary industrial equipment, when we're measuring at 40 degrees C, we're going to come up with what's called an ISO viscosity grade. Now, a lot of people think that ISO stands for International Standards Organization, but actually stands for equivalency. So we're going to come up with a viscosity grade classification for an oil. So let's say I've got an AW68 hydraulic oil. Okay? Well, let's say I've got an AW46. I'm going to come over here. I know that it's got anti-wear in it, but the viscosity is an ISO viscosity grade 46. So for a 46, what's the minimum and the maximum that it can be? It can be as low as 41.4 in our test of used oil, or as high as 50.8. If it's in that range, it's still considered to be in range for its viscosity. Now these guys have a oil that is actually a 68, but on the paperwork it's listed as a 46. So what's the range for a 68? 61.2 to 74.8. Okay? So because the information that is submitted on the sample, with the sample, and I'm not saying these guys did it, the information that was submitted with the sample, it has always been pulled from the equipment list. They're submitting samples online. Their equipment list has always said AW46, ISO VG46, but actually in reality, you know, they said, hey, no, we're putting 68 in everything. We used to have two different ones, but we just went to one so that we wouldn't, you know, have commingling or topping off of the wrong product. So because of that, they're getting a flag on their reports. Does that make sense? It's in the 3 or 4 range because of the fact that it's out of the viscosity grade. So that's just a matter of going back and making sure the equipment list is accurate, because every time you pull a sample, it's going to put that information that's in the database. Okay? All right, so we see typically hydraulics oils are going to be 32s, 46, 68s. Sometimes we'll get into gear oils. Gear oils will be typically a 220, 320, or a 460 gear oil. But that's how we use that ISO viscosity grade when we measure it at 40 degrees C. Now this is an equivalency chart, and I wish it was vertical instead of horizontal, but it'll still work. Because there's different ways, different lubricants measure viscosity different ways. But what we want to show you is, even though they measure it different ways, the numbers are different, but they're still the same viscosity. They would still pour, they would still flow at the same rate. So here's your ISO viscosity grade, okay? And here's your viscosity. Let's say that's an AW46 right there. So just remember that. We come over here, we've got a Society of Automotive Engineers gear oil. So for gear oils, they use this kind of a grade. And then we've got an SAE engine oil classification, and they use this kind of a viscosity grade. So the numbers are all different. But what I want you to see is if I've got an AW, instead of a 46, let's do a 68. I've got an AW68, and if I had an 80 weight gear oil, and if I had a 20 weight motor oil, if I poured all 3 of those, they would flow the same. They would have the same viscosity. So even though the numbers are different, this is called an equivalency chart. Okay? So let's say I had a 150 and a 90 weight and a 40 weight motor oil. 90 weight gear oil, 150 hydraulic oil, 40 weight engine oil. All 3 of those would be equivalent. When you poured them, they would flow the same. Does that make sense? Okay? So that's called a viscosity equivalency chart. Now this is going to show the difference between how a synthetic handles changes in temperature versus a conventional oil. So let's say I had an oil. We've got 2 oils here, gold and black. They're conventional oils, just petroleum oils. And one's a 220 viscosity, the other one's a 320. So this one's going to be heavier than this one. And then they both got a VI, a viscosity index of 95. Remember I told you the viscosity index, the VA, is an indication of how temperature stable that oil is. So if we take those two, they're going to be parallel because they're different viscosities. But as you change the temperature across the bottom here, what happens to those viscosities? They thin out, right? They thin out, but they never cross. They're two different viscosity grades, so they're going to be parallel, but they thin out. Now you introduce a synthetic, and it's a 220, okay? It's the same viscosity grade as the gold bar. What happens with the temperature when it's really cold? This one doesn't thicken as much. What happens when it gets warm? It doesn't thin out as much. That's one of the things about synthetics. They're more temperature stable. And because it's more temperature stable, what is its VI? It's 152, okay? In an ideal world, viscosity would just stay the same no matter what the temperature. But that doesn't happen in the real world. With a synthetic, you approach that kind of a theoretical world. So that's why you'll see synthetics are recommended a lot of times for environments where you have extreme temperatures, extreme hot, extreme cold, or you have a piece of equipment that you can't get to change it out. Synthetics are going to have a longer life. They're going to maintain that viscosity. All right, now we're going to have some questions for you, and this is going to be on viscosity. I'm going to have you select the viscosity. If I've got a high load, a heavy load on my equipment, do I want a heavy viscosity or a high viscosity or a low viscosity? Got a heavy load. I want to maintain that film strength. Do I want a heavy viscosity or a light viscosity?
High.
High? Who says high? Okay, good job. Yeah, because you want to maintain it. You don't want it to be squeezed out. Now what if you've got high temperature? Do you want to start out with a heavy oil or do you want to start out with a light oil? Heavy, absolutely right, because what's going to happen to that oil as temperature increases? It's going to thin out. All right, what if I've got high speed, you know, like a spindle bearing, something that's really turning with a lot of RPMs? Do I want a high viscosity or a low viscosity?
Low.
Low, okay. Very good, you guys did good. You're all now graduates of Viscosity University. You can pick up your diplomas later. Good job, good job. All right, let's talk about acid numbers. So you saw the importance of viscosity. We've got to maintain that film strength. This is one of my busy slides. I don't have to go through it. It's a titration method. We get that sample. We're going to titrate it with, if we're trying to do acid number, we're going to hit it with a base reagent. And we're going to put that in there. We're going to try to neutralize it. The old name for this, instead of acid number, was neutralization number. That's all we're trying to do. We're trying to neutralize that sample. Once we do, that's going to tell us how much acid is in that lubricant, okay? And so, what I need to know is, if let's say I've got that AW46 or AW68, a hydraulic oil. This is where we commonly use acid number. And let's say it's a brand new product. And that's one thing I want to encourage you to do if you haven't done. Whatever products you're using at your location, make sure you send in a virgin sample to the lab and say this is a new lube reference sample, this is a baseline reference sample, check the box, and what they'll do is they'll test that oil, brand new as a virgin oil. And then what will happen, since it's tied to your account, every time you get a report, all the numbers from that test result will be at the top. So every used sample will come in below that, but you can always refer back to that and say, hey, this is where I started. So that's how we're going to use these tests. We're going to say, where did I start? That's going to tell me what my flagging protocol should be. So for acid number, let's say on a hydraulic oil, a brand new hydraulic oil can be anywhere from 0.4 to 0.6. But let's use 0.5 because it's easy math. So whenever that doubles, okay, if it started at 0.5 down here in the green, when it started at 0.5, and whenever that doubles, what is that? That's 1.0. That's going to be a caution level, or what we call a severity 1. In our flagging protocol, we've got 0 is normal, severity 1, 2, 3, 4. 1 is a minor deviation, 2 is moderate, 3 is significant, 4 is severe. You will see those words that I just said, minor, moderate, significant, severe. You will see those in the comments. Anytime you see those words, you know that's a 1, 2, 3, or 4, because we use part of that to come up with the overall score. So, okay, we started at 0.5 new. We're at 1.0. That means that that's severity 1. Okay? If I go 4 times what it started at new, 4 times 0.5, what is that? 2.0. When you get to 2.0, we're going to tell you that's a severity 4. You have essentially oxidized that hydraulic oil. It's time to either drain and sweeten or get that product out of there. Okay? So rule of thumb on acid number, when you get to 4 times what you started at, and oftentimes it's 2.0, it's time to get that product out of there. Okay? So that's how we use that for the hydraulic oil. So that's what I'm saying. Well, now we're doing condition monitoring. Now we're getting into the oil analysis. Now we're looking at the data. We know how the test is run in layman's terms, but how do we use that data? And we need to have a baseline to look back to. Okay? So that's acid number. Now I will tell you there's some heavy-duty engine oil OEMs out there that are starting to use acid number for heavy-duty engine oils. And I get that. You know, I'm still old school. I like to use the base number because the base number will tell you how far you can go. So we're going to talk about that here in a minute. That was acid number. Let's talk about base number. Base number is what I typically used in my career when I was selling lubricants, and now that I'm in analysis, I've always used base number to say, what's the condition of that heavy-duty engine oil? Does it have any life left to it? Because base number is a titration. Again, this time we hit it with an acidic reagent, and we neutralize it. Once we neutralize it, we say, okay, how much did it change? So typically, if you run a new lube reference sample on a 15W40 heavy-duty engine oil, it's going to come back at about 8.5, 8 to 8.5 on our test results. Okay? So that's your starting point. Let's say 8 is your starting point. At that point, you've got a virgin product. It's fully additized. Okay? You've got all the additives in there that you need. Now we're going to start tracking it. So when it gets down to 50%, okay, the additive levels have dropped to 50%, we're going to say that's a severity 1. When it's got down to 25%, we're going to say that's a severity 4. So if we start at 8, what is a severity 1? %50 of the starting base number of the new oil. If we start at 8, what's 50%? 4, exactly. Okay? That's the initial flagging point. When I get down to 25% of what I started at, what's 25% of 8? 2, 2.0. Okay? When you get to 2.0, we'll say you've essentially used up the detergents, the dispersants in that oil. Okay? And it's time to change that oil out. Either drain and sweeten or change that oil out. So what I'm trying to share with you here is when you're looking at a report, keep these things in mind, these green and these reds. That's why you're going to have this PDF. You can look back at it at any time. But those are just the basic rules of thumb. So that's viscosity, acid number, base number. That's how we look at the condition of the lubricant. Now, I won't do this. This is for turbines, so we can skip over that. The next thing we're going to test for is contamination. And the most common contaminant we see is silicon, dirt, alumina silica, and then we see coolant, sodium and potassium. And everybody knows about the sodium and potassium, the primary inhibitors, the primary corrosion inhibitors in an antifreeze. But what about these other ones? Silicon, molybdenum, boron, phosphorus. Have you ever heard of those as being an indication for antifreeze? What will happen is they'll show up as silicates, molybdates, borates, and phosphates. And I'll show you that here in just a minute. So those are the secondary inhibitors. We'll see sodium and potassium first, but right on the heels, quite often what I see that comes again on a report, the first one in is molybdates. So when you see both of those, that tells you I've got a coolant contamination. What are some other contaminations that we see? Fuel. Fuel lowers the viscosity. Soot loading is unburnt fuel. It increases the viscosity. Then we see oxidation and nitration, which have byproducts from the combustion process. And then we see water contamination. Okay? So now we're going to test for all these contaminants. 98% of wear problems are directly related to contaminants. Abrasives, coolant, fuel, and soot. We've got a paper in our library. It's called the 4 engine killers. That's the 4 engine killers right here. Abrasives, coolant, fuel, and soot. Okay? And if you put the incorrect lubricant in there, that can cause a problem. And oxidation, nitration, we've talked about that. So those are the contaminants that we're dealing with. On dirt, we're going to look for silica. We're going to look for aluminosilica. And we used inductively coupled plasma, ICP. That's how we check for the wear metals. That's how we check for silica. That's how we check for alumina. It's detected through that elemental analysis, and I'm going to talk a little bit more about this in a minute. This is our ICP, and basically the sample just comes up through here, goes over the flame, and when it does, it flashes off into an array of colors. Each one of those colors represents an elemental wear metal, and then the intensity of that color is converted to parts per million for that particular element. Okay? It only takes about 60 parts per million of dust to dust an engine. When I worked in the oil field, we got our first diesel engine in. The guy took us in the shop, and he showed us a tablespoonful of soot or dirt, and he said, if I threw this into this engine, he said it would crater this engine. So it doesn't take a lot of dirt, and so we're going to measure that. We're going to find dirt by aluminosilica, but we're going to remember silica is also silicon that could be part of the anti-foam additive. So if it's less than 20 parts per million, it's probably not dirt. Once it gets above 20 parts per million, aluminum starts increasing. We'll look over and we'll see iron wear. We know we've got a dirt situation. Okay? All right. This statement here, I really try to stress this each and every time. Approximately 50% of all premature preventable engine failures are due to an issue with the cooling system, or the coolant, if you want to be more specific. So if that's the case, why wouldn't you want, if you're doing enginal analysis, why wouldn't you want to do coolant analysis? You know, you're only talking a couple samples a year. Why wouldn't you want to have the whole picture? Because the oil and the coolant, they are related, okay? So let's go ahead and run that coolant, and we can prevent a lot of these engine failures. And how are we going to identify it? Sodium and potassium. Secondary inhibitors are the molybdates, borates, silicates, and phosphates. Okay? Now, our chief operating officer, when he would teach this class, he would put this slide in. How do you make asphalt? What are the components of asphalt? When we're driving down a road, we're driving down an asphalt road, what does it take to make asphalt? What do you got to have? You got to have oil? You got to have stone, you got to have rock, you got to have dirt, whatever. Okay, what else? Heat, okay. How are we going to bind that all together?
Polymers.
Say again?
Polymers.
Well, it's not a polymer, it's actually, huh?
Mix it together.
It's glycol. Glycol. Okay, that's how they make asphalt. Well, think about this in an engine. What if I've got an engine and it's running at a high temperature, like the gentleman was saying, okay, and I've got gravel, I've got dirt in there, okay, and then I've got oil that's circulating in that engine, and all of a sudden I get coolant in there, I get glycol in there. What's this engine doing? It's making asphalt, okay? So that's what happens when you get coolant into an engine oil. It will actually drive up the viscosity, and it'll start plugging up parts of that circulating system and cause you problems, okay? So that's why coolant analysis, I think, is a huge thing. And we can detect coolant contamination at extremely, I told you, a sewing thimble full of coolant in 11 to 14 gallon reservoir, we're going to see it. So we can see it at incredibly low levels. This is the FTIR, Fourier Transform Infrared Spectrometer. This is a quick test that we do when we first get a sample in. It allows us to see, is there any soot contamination, any water contamination, any oxidation, any nitration. And the way that it simply works is we take that sample and we run an infrared light through that sample. And what happens is each one of these contaminants has its own wavelength. And that wavelength is like a fingerprint. It identifies it. So let's say we've got a sample and we've got a lot of soot in it. okay? So we got 6% soot in it. What's going to happen is when we run that light through there, it's going to pass through that sample, but less light is going to get to the receptor because of the fact there's so much soot in there, okay? And so then we're going to identify that soot and say, yes, we have a soot contaminant, and based on the level that left the light beam to where it got to the detector, the lower value, that's going to determine how severe that soot loading is. Is it 2%, 3%? And for soot loading, we're going to shut down an engine at 7%. We're going to say that's a severity 4, okay? So that's how that is used for a quick test of 4 contaminants that we might see. This is a gas chromatography, and what we're going to use this for is we're going to check the fuel. Okay, so we're going to check a sample. This is what's amazing about this piece of equipment. Think about this. We're taking a used oil sample, and we're going to look for a fuel, which is a petroleum product, typically, inside of that oil sample. You're looking for a petroleum product in a petroleum product. This thing is really amazing. If you open the door on this, there's a small little capillary tube that's in a coil, very thin. So what happens is we atomize that sample, we run it through that coil. That coil will actually absorb whatever type fuel it is. If it's biodiesel, petroleum diesel, gasoline, and then it'll release the information to the computer, and it says, okay, for petroleum diesel, this is the peak, and the area under this peak, that's the percentage of fuel dilution that you have, 3%, 4%, 6%, whatever. If it's got biodiesel, that peak would show up at another place on the x-axis. If it's got gasoline, it would show up at another place. But it calculates the area under there and it tells you what your fuel dilution is. That's how we do fuel dilution. Now, why is fuel dilution important? Well, when you're getting into analysis, you're going to say, what are the severity levels? What are the flagging points? Okay, so I put this slide in here. Let's say I had a severity 1 of fuel dilution, that 2 to 3.5% of that sample had fuel in it, okay? What would cause that? Well, you could come over here and the analyst might say excessive idling. Now, what if I had it at severity 2, 3.6 to 5%? They may say excessive idling, possible cracked injector problems, okay? And so one of the things I love about our team, our data analyst, is they really drill down. You know, they don't just tell you, hey, your viscosity is low. They say your viscosity is low due to fuel dilution, and we suspect you've got excessive idling or a possible cracked injector. So I feel like our comments, they really drill down versus other labs, okay? Now, one thing to keep in mind when you get fuel dilution, the little note down here in the red says, watch for decrease in viscosity, friction-related wear, diluted additive metals. If you get that fuel dilution in there, 5, 6, 7%, that viscosity is going to go low, and what's going to happen? You're going to see your wear metals increase. Viscosity is going to decrease. So just be mindful of that when you're looking at a report. This is a Wilks soot meter. Quite simply, all you're doing is looking at the unburnt fuel, the soot that would be in a used oil sample. We simply drop that oil drop onto that little window, and it'll come back and say, hey, you got 4.5%, 5% soot loading, unburned fuel that's in this sample. This can be accurate up to as high as 10%. So that's how we measure the soot. All right, and then here's some possible causes. Severity 1, severity 2, severity 3, severity 4. You can go over there and see what we say, but a lot of times these same comments will show up on your reports. Now, something to keep in mind when you get soot loading, watch for an increase in viscosity, and then you're going to see some upper end wear, and just be mindful that a failure could occur. So you want to stay on top of your soot loading. Oxidation, nitration, yeah.
Isn't soot is extremely hard, right? Soot particles? They're almost as hard as diamond, I've heard.
Soot?
Yeah. Is that true?
Yeah, I don't have the slide that my boss has, but he shows the comparison of hardness. And like you said, there's a chart that takes you down through there, and soot is like that. It's a very abrasive particle, but what makes it even worse is the little soot particles. That's why you have a dispersant in the oil. The soot particles want to come together, and then they make larger soot particles, and they're very, very abrasive. Yeah, I'm not sure what it is on the hardness scale, but I know it's pretty high there. Good point. Okay. Oxidation, nitration. The way I separate oxidation, nitration, oxidation typically happens with heavy-duty diesel engines. Nitration typically happens with natural gas engines. Anybody doing anything with natural gas engines? Okay, that's usually nitration. That's what we see there. Their flagging protocol is when you get to 25, that's the initial flagging point. When you get to 30, that's the condemning limit. Okay, so just keep those numbers in mind. 25 and 30 for either oxidation or nitration. When you see those numbers get to that level, time to change that product out. Water, we typically just do a crackle test. That's where you drop the oil drop onto that hot plate at 150 degrees C. The analyst is so good. He's seen it so much, he can tell you, he can guesstimate how much water is in a sample. If you want to know exactly how much water is in a sample, we used to have the steel mills that would send in samples and say, hey, I want to know exactly how much water is in here. I want to know how much is dissolved water, how much is emulsified water, and how much is free water. I want to know all the water. Well, you're going to run what's called a Carl Fisher, okay, and get those test results. But the crackle test is just a way to say, hey, you know what? It's accurate up to about 5,000 ppm. I went to a coal mine one time. They had a sample, and they were getting ready to send it in. They said, Henry, this thing's really cloudy, milky looking. Have we got air in it, or have we got water in it? And I said, well, a quick way to check is you take a spoon, you take a syringe, which I carried in my car. You know, I got an engineer's test kit. I take this spoon, this syringe, and a cigarette lighter, and we put that in there, and I heat it up. If it's water, what's it going to do? It's going to pop and crackle and sizzle, sounds like bacon. If it's air, it's not going to do anything. It's going to dissipate, okay? So that's a quick crackle test. That's essentially what we're doing in the lab. We're just putting it on there, hitting it with 150 degrees C and see if we can cause it to pop and crackle, and then guesstimate how much water there is. The joke about that test that I do in the field is called the field crackle test. The joke is that when you get back home, make sure you don't take the spoon, you don't take the needle, you don't take all that stuff and put it in your office desk, because somebody will probably be doing a drug test on you. But that's the crackle test that you can do in the field to determine, do I have air in my oil or water in my oil? All right, so this is testing for wear and debris. This is the third set of test data we're going to look at. And then shortly after this, we're going to talk about applications, and then we're going to do some data interpretation. So, testing for wear and debris. We're going to talk about elemental analysis. That's where you get the 24 elements on the report. We're going to talk about optical particle count, particle quantifier, or what we call PQ, and then analytical ferrography. So now we're starting to look at the wear and the debris. There's different ways to do it, different ways to do it through a spectrometer, but we use, you got arc spark, you've got ICP, inductively coupled plasma, and then you've also got X-ray fluorescent. This isn't as repeatable and reliable as ICP, so we chose ICP because it's accurate, it's reliable, we feel the data is good, consistent. X-ray fluorescence is the best you can do, but the problem with that is it's very expensive. So this seems to fit the customer base that we deal with, and so we do inductively coupled plasma. So what's it look like? And I would encourage you, if you guys ever get to Indianapolis, you're more than welcome to stop in and ask for a lab tour. Anybody can give you a lab tour at any time. But this is probably one of my favorite pieces of equipment. This is the ICP, inductively coupled plasma. So what happens? We bring in a tray, a test tube tray full of used oil samples. We suck it up, it comes through here, we hit it with an argon gas, so we atomize it, make it like a mist, and then it travels through here and it hits this flame. And when it hits this flame, that's a plasma flame. And somebody told me there's 3 states. There's liquid, solid, and gas. And people think that plasma may be a 4th state. So anyway, the thing that I tell people about it is look at that temperature. That flame is at 9,000 degrees C, 12,000 degrees Fahrenheit. That's roughly the temperature of the face of the sun. And I could put my hand on that little window and it would just barely be warm. It's just a crazy flame. So anyway, you pass that across there, that atomized, that mist, and it makes this rainbow of colors. Well, each one of those colors represents one of those 24 elemental metals that you see on the report, okay? It could be iron, it could be nickel, it could be copper, whatever, okay? Or it could be an additive. It could be potassium, a corrosion inhibitor. So it could be all these different things, but they've all got their own color, which identifies them, and then the intensity of that color, the brightness of that color, is converted to parts per million. So you know how much of that element is in that sample. Now, once we've run all of these tests for metals, we're going to break them into categories. So these are the wear metals. So when you're looking at a report and you're looking at those 24 elements across the middle of that report, iron, chromium, nickel, aluminum, copper, lead, tin, cadmium, silver, titanium, and vanadium, those are all going to be wear metals. Now, the orange is going to be the contaminant metals. Silicon, what did we say silicon was? Dirt, very good. Sodium and potassium, what's that? Okay, that's a coolant contamination. Then we get into the multi-source. Molybdenum, antimony, manganese, lithium, boron. When we see lithium, that's usually coming from a grease. When we see moly, it says multi-source. Moly can be a corrosion inhibitor, can be a friction modifier, can be an antioxidant. So it's a multi-source metal. And then the last group we see in the green is the magnesium, calcium, and barium. What did I tell you that is? That's part of the detergents and dispersants in your heavy-duty engine oils. But magnesium, calcium, barium. And then phosphorus. What if we see phosphorus by itself? What do we think that is? Extreme pressure additive. We find that in gear oils. What if we see phosphorus and zinc together? That's your anti-wear in your hydraulic oils. Okay? So that's how we're using this data. That's how we break it down. That's how we report it back to you. Now, the smallest particle size the human eye can see is 40 microns. We've already talked about that. So you've got a lower limit of visibility. But the stuff that's causing us problems is down here in the 3 to 5 micron range. Okay? So stuff that we can't even see is causing a lot of our problems. Okay? All right. This is the optical particle count. Remember I told you when we get a sample in, we're going to shake it up. Well, for the particle count, we're going to shake it up for 15 minutes, and then we're going to take that oil and we're going to pass it up through this tube. And as it does, we've got a light that goes through there. The light will hit every particle that's in that sample, and it will count it. It will not only count the number of particles, but it'll put it into these size ranges, greater than 4 micron, greater than 6, all the way up to greater than 100 micron. Once that happens, then we get our ISO cleanliness code, okay? And so the ISO cleanliness code, let's say we had a 16, 14, 11. Remember I told you the higher the number, the dirtier the oil? This is how we're going to use that ISO cleanliness code. Let's say I had a 16, 14, 11. 16 tells me what? Tells me that there's 320 to 640 particles that are greater than 4 micron in that sample. 14 tells me what? There's 80 to 160 particles that are greater than 6 micron. And then the 11 tells me that there are 10 to 20 particles that are greater than 14 micron. Okay? So then we use the 4 micron, the 6 micron, and the 14 micron numbers from our test result. Remember, I told you it does all of these, but we only take out the 4, the 6, and the 14 to come up with what's called an ISO cleanliness code. Now what I want to ask you is what happens if that number that was 16 goes from 16 to 17? Or let's take it this way. We go from 16 and we filter it and it goes down to 15. What have we done to the number of particles? Has it increased or decreased? Decreased. Yeah, it's cut it in half. So each time we move one of these levels, we're either cutting it in half or we're doubling it. Okay? And so that's part of the ISO cleanliness code. That's how you use that. All right, this is the PQ. This is the particle quantifier. Let's say we had a gearbox, and you're going to send in a sample, and we're going to take that sample, and we're going to put it on this little platform, this little machine, and it's going to have this rotating wheel, disc, on top of it. And we put the sample in there, and it rotates it from 12 o'clock to 3 o'clock to 6 o'clock to 9 o'clock back home. This machine generates a magnetic field. At each position, the amount of ferrous material and the size of the ferrous material in that sample will cause a deflection in that magnetic field. Based on the severity of that deflection, we come up with what's called a PQ index. The higher the PQ index, that means the more ferrous iron wear that's in that sample, as well as its larger particles. I had a lady one time that sent in a sample on a gearbox, and she was seeing her iron increase with every sample. It was going up, up, up. And then all of a sudden it started coming back down. And she called me and said, Henry, she says, did my problem go away? And I said, no, ma'am. I said, you should have been running the iron test like you were, but you should have also ran a PQ. Because what happens is with the ICP that's measuring the iron, one of the limitations to that, and I forgot to mention it, is it's only about 5 to 10 microns or smaller than it can see. So what happened to her was as the iron was going up, it was increasing, but the chunks were also getting larger, the particles. So once they got above 10 microns, the ICP couldn't see them anymore. And I said, if you'd been running a PQ, that PQ index would have kept going on up, and we would have been able to tell you, hey, your problem's still there, and it's absolutely getting worse. So that's why we use the PQ index typically on gearboxes, and sometimes we will use it on transmissions as well. This is analytical ferrography. Takes about 2 to 3 years for an analyst to be trained and be qualified to do this. This is the only test that we will get a result back, and if it's at a severity 3 or 4, we might call the customer and say, hey, you need to shut this down immediately. Okay? This is the only test we'll run that will do that. But this test is so involved because once we get that sample, we make a slide, and there's magnets underneath that slide, and you'll have rows of metal particles, okay, based on different sizes. And so they're going to look at those, and anything that's not ferrous, it's just going to drop anywhere on the slide. So he's going to look at that slide, and then this is what he's going to see. He could see any one of these 8 different types of wear. I kind of get it. I think I kind of understand some of these, like rubbing wear. That kind of makes sense. You know, if you got a back and forth, that striation, that makes sense. Abrasive wear, that's dirt. We've seen that. Cutting wear. This would happen if you had a shaft and a mating component, and if that shaft got a piece of dirt or something embedded in it, it would act like a lathe, and it would start cutting pieces out, little curls. Okay, that's cutting wear. Spheres, remember what I told you the spheres come from? When you have metal removed from a component because of a little piece in there that won't break, won't separate, causes a fissure, you get that hot melting metal comes out, it rapidly cools into the spheres, you know that you've had some type of metal removal. But this is where it gets complicated for me. You've got this snowflake, you've got this snowflake. According to them, this is spalling wear, this is laminar bearing wear. I can't see the difference. But it takes about 2 to 3 years, and if I put this in front of one of them, they could absolutely tell me the difference. The last 2, that makes sense, that's rust. And then over here, the last one is the black one. There's been some type of a high temperature event. But when you're into analytical ferrography, this is an add-on test. This isn't a typical test that we typically run. But based on the result of an oil analysis, we may say, we suggest you run analytical ferrography, and then this is a test that would follow and what they would actually be looking at. Okay, all right, let's take a break. Applications, we'll come back and do applications, and then we're going to jump into a little bit of data interpretation and put to use what we've learned here today.